Okay, so the other snubber that we're going to look at is a turn-on snubber. When we look at the turn-on snubber, we see that the capacitor is gone. And what we now have is an inductor in that position there. Now a capacitor does not allow an instantaneous change in voltage over its terminals. An inductor does not allow an instantaneous change in the current flowing through its terminals. So we can use this inductor in the same way as the capacitor was used for turn off. When the voltage is going to increase over the device, we can now at turn on keep the current within safe limits so that the device does not experience a too high turn on. We can also use wave shaping here to minimize the power that is dissipated in the device. So it's got a two-way it's a two-way answer for a problem. One device limiting the rate of rise of the on-state current to keep it below the critical, and also to minimize the power that is dissipated in the device. Now both these things that I've just said can destroy the device. Here we still have the RL load, and we still have our flyback diode there. When will the diode switch on completely? Or when will it switch on? Or when will it switch off? Which one is it now? It's the turn on snubber. So the current was flowing like that. And now we want the current to stop flowing like that, and we want the current to come through the switch. So we are talking about that point there when the current through the transistor has increased to its maximum value. So at T1, that is the point at which the diode switches off. What was it when with the previous one? That was when T1 was when the diode switched on. Here is when the diode switches off. Once again, we now understand that we are going to determine the ratio from T1 to T2 for optimum, and we are going to have, instead of Vt, we need an equation for It, and we need an equation for Vt. But now Vt is the one that has got the linear fall. It is not really completely linear, but it makes our life much easier if we assume linear fall. And the answers that we get are close enough so that that assumption is okay. So from the graph of the transistor voltage, we have that Vt is equal to V minus T over T2 times V. And you understand where it comes from? Because we've just done it for the current, and then the current was had the linear fall, and our equation is y is equal to mx plus c. If we now apply Kirchhoff's voltage law to the circuit, remembering that the freewheeling diode is on up till T1, we get that V is equal to Vt plus VL. That Vt there is equal to V plus VL. Do you agree with me? Kirchhoff's voltage law. Thus up to T1 we can say that the inductor voltage is equal to V minus Vt. At the time T1, It is equal to I. We are now up to that point there. At T1, It is now equal to I. we can at T1 determine the magnetic flux of the inductor, and that is given by, what is the Greek symbol here? Epsilon. Is it epsilon? Phi, C, PSI, C is equal to Li is equal to the integral between 0 and T1 of VL dt. If we substitute equation 6.9 and 6.10 into equation 6.11, we can determine that Li over V is equal to T1 squared over 2T2. And that gives us an equation for the inductor, and that is L is equal to VT1 squared over 2IT2. Now we need an expression for the switching energy loss in terms of VI, T1 and T2. Please change that E to a W in your book. The switching loss W by definition is equal to the integral of VI dt. We need an expression for IT up to T1. From the expression for the instantaneous voltage of an inductor, V is equal to L di dt, we get that IT is equal to 1 over L times the integral of VL dt. Substitute equation 6.12 into equation 6.14, that is the one for the inductor. And then substituting equation 6.9 and 6.10 into equation 6.15. If we solve for that, we get an expression for IT, and that is equal to T squared over T1 squared times I. Thus, the switching loss, VI, we get from 0 to T1, plus we get from T1 to T2. So you can see that here we've got a different expression for I than what we have there, but the voltage is still the same equation, because for the voltage we have this equation running right through. So from here to T2 we multiply I with that of Vt, and here we've got that exponential curve here for IT times that same equation for Vt. If you follow all of the integrations here and the simplifications, you get that the energy is VI T2 over 2 minus 2T1 over 3 plus T1 squared over 4T2. But the energy that is stored in the inductor there is already lost, because if we now switch off this device, then that current is going to drop to 0. And the energy that is stored in here is a half Li squared. So the same procedure as just now. We must then say that the total energy is equal to the inductor energy plus the energy due to switching. So we have that the energy stored in the inductor is equal to a half Li squared. We have an equation for L. We fill it in there and we get VI T1 squared over 4T2. So when we add of all of this together, we get that equation. Once again, you can see the a quarter plus a quarter gives us a half. For a minimum loss, dt, please change that to omega. Omega total is equal to 0. The VI's don't care. There's no T1 in that one. Minus 2 T1 over 3 becomes minus 2 over 3 when I've got d dt1. And then I get that T1 is equal to 2 over 3 T2. Does it ring a bell? So, worked example, a transistor has a switch off time of 3 microseconds and carries a current of 60 amps. The supply voltage is 120. Determine a turn-on snubber inductor for the transistor. Design the inductor for minimum loss in the transistor. And so we get that T1 is 2 over 3 T3. So since the this is wrong, that must not be switch off, it must be switch on. The transistor has a switch on time of 3 microseconds. So for minimum loss, T1 must be equal to 2 microseconds. If we fill off all of that into this equation for the inductor, we get 1,333 microhenries. Now, did you notice all the similarity? The reason for that is because of the principle of duality. The principle of duality. And we can use this principle of duality to our advantage in engineering. The principle of duality applied in electrical engineering means that if a situation viewed on a voltage basis is analogous to another situation viewed on a current basis, or vice versa, then the equations relating to one situation can be derived from those of the other merely by a routine interchange of the quantities or concepts. Thus, Ohm's law may be written as V is equal to I times R, but it can also be written as I is equal to V times the conductance, G. The second equation is obtained from the first by interchanging voltage V, current I, and replacing the resistance by conductance G. Quantities interchanged in this way are said to be dual elements, and the two equations are dual equations. In a similar way, the equations V is equal to L di dt and I is equal to C dV dt are called duals. Voltage and current are once more interchanged, and the inductance L and capacitance C are the two new dual quantities. The virtue and justification of this procedure is that when duals have been defined from one pair of equations, the same duals apply in another pair of equations. This has already been done for the above for voltage and current. By working with dual quantities, it is possible to recognize that many laws of physical phenomena occur in pairs, and it becomes possible to discover new or at least unfamiliar relations by direct analogy. Further, when the solution of the dual of a problem is known, the solution of the problem can be written down at once without doing a derivation. Now you can use this to your advantage. If I in the test or an exam ask you to do the derivation of the one that you do not know, then you state the principle of duality. You say which are the dual equations and what are the dual quantities. Do the derivation for the one that you know, and in the end just say applying the principle of duality and write down the formula that you should have derived. I did do it once. Not one student answered it in that way. But maybe this time, if I ask it.